Okay, in this video we're going to look at projectiles. So a projectile is something that you're throwing. So a projectile could be a rock or a missile or an object. A missile is one that they quite commonly use that language, a missile. So it's not an actual tomahawk missile being chucked at anybody. It is just an object that is being thrown. So a missile, an object, a particle, a ball, anything at all that is being thrown. So in all projectile motion, the most important thing is to treat the horizontal and vertical motion separately. Now this may well be different than the way you do it in physics, so we'll just have to see. So the horizontal velocity of a particle is constant since there is no force acting in this direction. This is what's called a mathematical assumption. We're dumbing down the situation so that we can manage it. So in reality, horizontally there'd be air resistance and different resistances and so on. But it would be slowing the thing down. But as far as we're concerned, there's no horizontal. The horizontal velocity is going to be constant throughout. The vertical motion, however, because we're acting vertically, we have the force due to the acceleration due to gravity. So that will cause the velocity to be changing in the vertical motion. And in some cases, we can use the I and J vectors to describe the motion, and we'll see that as and when we come to it. This example says a particle is projected horizontally with a speed of 14.7 meters per second. Find the horizontal and vertical displacement of the particle from the point of projection after 2 seconds, and then find how far the particle then is from the point of projection. So we'll do a wee diagram here just to show you what's going on. So first of all, this thing is starting with a velocity of 14.7 meters per second horizontally. So if you imagine it's going to go out, and it's going to go out, and then it's going to fall down this sort of direction. So that's really what is happening. So we're going to look at the horizontal displacement, and then we're going to look at, for a wee equation for the horizontal displacement, and we're going to look at the vertical displacement as well. So horizontally, first of all, your displacement S is just basically distance equals speed times time. So your speed is 14.7 and your time we're going to say is t seconds. So it says after 2 seconds. So after 2 seconds, S is going to be equal to 14.7 times 2, which works out to be 29.4 meters. So that's what's happening horizontally. Okay, vertically. Okay, if we look vertically, there's no speed vertically. So vertically, my initial velocity is 0, and I'm going to say anything going downwards is positive. So my u is equal to 0. My acceleration is the acceleration which is due to gravity, so it's 9.8 meters per second squared downwards. And my time is, just to call it t, it's just equal to t again. And we're going to find our displacement. So S is equal to, the equation we're going to use is ut plus a half a t squared. So in this case, it's going to be ut, so 0 times anything is 0. A half times the 9.8 is going to be 4.9 times t squared. So your S just works out to be 4.9 t squared. So we'll just say when t is equal to 2, S is equal to 4.9 upon 2 squared, which means your S works out to be, and that would work out to be 19.6 meters. So we've now got that this thing is 29.4 meters, horizontally, and then downwards it is going to be 19.6 meters. So what we want to find is the overall. So we're just going to call that d. This is the overall distance, and this we're going to use this dead simply using Pythagoras' theorem. So d is going to be equal to, it's on the hypotenuse, so it's the square root of our 29.4 squared plus our 19.6 squared. and we're going to square root and press equals on that. So square root of whatever I have just said, let's just check it, 29.4 squared plus 19.6 squared, press equals, and what I've got to 3 sig figs is 35.3 meters to 3 sig figs. So that is our first example done. So treat your horizontal as one part, work out your horizontal displacement, and treat your vertical as another part, and work out your vertical displacement, and then combine those two using Pythagoras' theorem just to find your overall distance gone. In this example, it says a particle is projected horizontally from a point 44.1 meters above a horizontal plane. The particle hits the plane at a point that is horizontally 39 meters from the point of projection. Find the initial speed of the particle. Okay, right, so it's quite a different question than the last one. Let's just do a diagram, see what's going on. We want to find the initial speed. It's projected horizontally, so it's just projected like that. It is 44.1 meters above the ground, and it lands at 39 meters from the point of projection horizontally. So it goes out like this and it goes down. So if I was doing this, I would be drawing this wee diagram out before I got started. So I'm gonna do the vertical this time first. So vertically, my initial speed vertically is 0. My acceleration is 9.8 downwards. My displacement is 44.1 downwards. And I want to find the time that it takes for it to go. Because if I can find the time that it takes, I can find the initial speed, because I know this is 39 meters horizontally, and if say I found the time was 10 seconds, then I could find my speed, because distance, remember, is equal to speed times time, so I can use these two things to find it. So that's why we're finding our time here. So to find your time, we're just going to use the constant acceleration equation, s equals ut plus a half at squared. So in this case, that's going to be 44.1 is equal to, and that's going to be 0 times anything is 0, so ut is going to be 0. A half times the 9.8 is going to be 4.9 times the t squared. Wee bit of working out then, let's just check this on a calculator. 44.1 divided by 4.9, 44.1 divided by 4.9 works out to be 9. So I've got 9 is equal to t squared, so my t is equal to 3. You don't have to write plus or minus 3. You know it's positive 3 seconds, minus 3 seconds wouldn't make any sense. Then what we can look at is horizontally. So horizontally, and we're just saying distance is equal to speed times time. And we now know the distance was 39. Speed is u, and our time we now know is 3. So u is equal to 39 divided by 3. So u works out to be 13 meters per second. Read the question, says find the initial speed of a particle. We have done it. That is it. Okay, the next example says a particle is projected horizontally with a velocity of 39.2 meters per second. Find the horizontal and vertical components of the velocity of the particle 3 seconds after projection. Find also the speed and direction of the motion of the particle at this time. Okay, this is probably an easier example really. We start off with it's projected horizontally with a speed of 39.2 meters per second. And I'm going to do the hard bit first, which is the vertical bit, vertical motion. So my u is clearly 0. My a is 9.8, and that's downwards. My t is 3 seconds, so v is equal to u plus at. So v in this case is just going to be 0 plus 9.8 times 3, so v works out to be 29.4 meters per second. horizontally, remember what we said at the very start of this video? We said that there's the horizontal velocity, horizontal component of the velocity, or the speed horizontally, is going to be constant. So horizontally, your velocity is just going to be equal to 39.2 meters per second. Because it started as 39.2, it's still going to be 39.2. It's going to be 39.2 horizontally all the way through this question. So what we can now do is do a diagram. So our diagram is going to be like this. So you've got the 39.2 going horizontally. That was our meters per second. You've got the 29.4 going vertically. And then what you want to find, I'm going to say this is my V is going this way, and we'll also have to find the angle. It says find the speed and the direction of the motion of the particle at this time. So we've done the first two bits, which was find the horizontal and the vertical components. We've done that. We're now on to finding the speed and the direction at this time. So V is very easy. V is just going to be equal to, by Pythagoras, it's going to be equal to 39.2 squared plus 29.4 squared. Do that on your calculator, and I have got a very nice answer. I'm just going to check it here. So square root of 39.2 squared plus 29.4 squared, press equals, and square root of all that, and it's going to be 49 meters per second. Okay, so very nice. So I've engineered this question basically so it will give you a nice answer. Tan theta will then be equal to, tan, remember, is equal to opposite over adjacent. So in this case, it's going to be 29.4 divided by 39.2. And then your theta is equal to tan to the minus 1 of that, whatever it was, what I just said, 29.4 over 39.2. So my theta works out to be 36.9 degrees. That's to 3 sig figs. And quite important, this last wee bit, just say below horizontal. Apologies for my bad handwriting. So there we have found our V is equal to 49 meters per second, and our angle is 36.9 degrees below horizontal. Okay, this is an example where we've got our I and j vectors involved here. So it says at time t is equal to 0, a particle is projected with a velocity of 2I. So I, remember what I looks like if you have a Dewey diagram. I is the unit vector, which is 1 to the right, and j, remember, is a unit vector which is 1 vertically, up. So this thing is starting with 2I. So it's starting just going 2I horizontally, so it's completely going horizontally, this thing. So I get rid of that, that's a bit of a mess. So completely horizontally. From a point with position vector 10I plus 90j meters, find the position vector of the particle at t is equal to 4. So we'll not worry about this bit to start with. This will come into play at the very end. We're just going to see what happens as this thing moves. So, vertically, do it and get it out of the way. It's the awkward bit. So vertically, your u is equal to 0. Your a is equal to 9.8, and that's going to be meters per second, and that's going to be downwards. Your t is 4, because it was after 4 seconds, and s is what we're going to try and find, so s is equal to ut plus a half at squared. So in this case, I'm just going to say that is, and there's another way I could do this, I will show you in a wee second. This is equal to just 0 plus, and it's going to be 4.9 times 4 squared, which works out to be 78.4 meters downwards. Okay, so it's downwards, 78.4 units downwards, i.e. we could say that is equal to minus 78.4 j meters. Right, just to show you another way that we could do this, we could say your U is equal to 0, your A is equal to 9.8 meters per second. Sorry, I made the same mistake. Your A is equal to minus 9.8 J meters per second. Your T is equal to 4, and then your S is equal to, vector S is equal to U times T plus a half times your vector A times T squared. So your vector S is equal to, it's going to be a half times the 9.8 J square, J, so it's going to be minus 4.9 minus 4.9 J times the 4 squared. So your vector S is equal to minus 78.4 J meters. Okay, just to show you there's two ways of doing that same thing. Right, so we've done the vertical component, I should say. Now we're going to look at the horizontal component. So just say horizontally. And horizontally, you're just going to say your S is equal to 2 times the 4. So it is equal to 8 meters. And i.e. that is the same as 8I meters. Or, just to show you another way you could have said that, you could have said your vector S is equal to 2I times 4, so it is 8I meters. So just to show you there's two ways of doing that one as well. So that means we've got our, it has moved 8I across, it has moved 8I, and it has moved minus 78.4 J. So that means your final position vector is going to be equal to, let's think back to what our initial starting point, it was 10I plus 90J. You've now moved another 8I and another minus 78.4 J. So when you do those, put those together, you're going to have 18I, and then it's going to be plus 11.6 J, and that's going to be meters.